Okay, so here is our matrix that we put into row echelon form. And so we're now going to put this into reduced row echelon form. So reduced row echelon form. And this is much easier to do than the kind of previous method that we did to get to row echelon form. And you'll see how reduced row echelon form is different. But for starters, each column will only have a single 1, or it will be all zeros. But the benefits of a reduced row echelon form are that it allows you to just read off solutions to simultaneous equations, and it also allows you to easily consider whether a set of simultaneous equations is consistent or inconsistent, and it allows you to find out the rank of a matrix, which I will soon cover, hopefully, in later videos. Okay, so the method to find the reduced row echelon form of this matrix is as follows. Actually, I've copied down this matrix wrong. Should be a 0 here. Okay, so we start off with the third row this time, and we want to make the kind of, so you can see how the third row, the leading 1 is in the third column. So now what we want to do is make sure that the elements above this leading 1 in the third row are 0. So we want to make this element here 0 and this element here 0. And the way that we're going to do that is, first thing we're going to do is we're going to do row 2 minus row 1. Obviously, we still only have to do elementary row operations, but the matrix that we'll end up with, row 3, but the matrix we'll end up with when we do this is 1, 1, 1, 0, 1, 0, 0, 0, 1, and then 3, 0, 2. If we then do the same with the third row and the first row, so we'll do row 1 minus row 3, because there's a 1 here, we don't need to multiply row 3 by a scalar. So that'll give us 1, 1, 0, 0, 1, 0, 0, 0, 1, and then 1, 0, 2. And kind of similar in a way to Gaussian elimination, we can now ignore the third row and focus on the second row. And now what we want to do is get rid of this 1 here, because that is above the leading 1 in the second column. And so again, if we just do row 1 minus row 2, we will get 1, 0, 0, 0, 1, 0, 0, 0, 1. And then on the right hand side of the vertical line, we will have 1, 0, 2. And then because we're now at the top column, we don't have to carry out this process again. And that's it. We have now put the matrix into reduced row echelon form. So we've done it. And if you look closely enough, you'll see that the portion of the matrix to the left of the vertical line is actually the 3 by 3 identity matrix. And like I said before, using this method, we can easily read off the values for our variables in our simultaneous equation. And I'll show you how. So this first column here, that represents the coefficients of the variable x. The second column are the coefficients of y, and then the third is z. And then you can imagine this kind of vertical line as the equal sign. And then these are the constants. I'm just going to write C for constants. And so then if we look at the third row, if we start off with the third row, we have 0x plus 0y plus z is equal to 2. And so this tells us z equals 2. Similarly, from the second row, we can get that y is equal to 0. And then from the first row, we can get that x is equal to 1. And that's it. We have solved the simultaneous equation, and we have put the matrix into reduced row echelon form. And so before I end this video, I just want to quickly write down the properties of a matrix in reduced row echelon form. Again, as you can see, I have written the 4 rules for a matrix to be in reduced row echelon form, and they are: every non-zero row begins with a leading 1, a leading 1 in a lower column is further to the right, 0 rows are at the bottom of the matrix, and every column with a leading 1 has 0 elsewhere. So essentially the only new rule is rule 4.